Okay, so picking another tool out of the toolbox. So I think this might be probably the final one we're looking at in this lecture. We've got binary space partitioning, right? So this is another kind of approach that comes from roguelikes, but it's applicable to kind of level design in a whole range of different games. So yeah, this is the kind of stuff which was literally used in the game Rogue and kind of early examples. It's been around for many years. So what we're doing here is we've got some idea that we've got some game space and we want to basically divide it up into room-like levels. So rather than kind of doing bottom up, which we saw with Cellular Automata, where we're kind of like taking some kind of, looking at the individual region of this game space and doing a simulation to make a pattern, or doing a random walk around it to make a pattern, we're kind of having a top-down approach here instead. So we're starting off with some region of space, probably 2D, but we can actually do this in 3D as well. It generalizes. We're taking that region and we're kind of recursively partitioning it. So we're saying, okay, that region A is made up of two regions, B and C. And then recursively, we're taking each of those regions and again dividing it up. So B got divided again vertically. With C, we can randomly choose which way we're going to be doing this. So we can divide a region vertically or horizontally, but we're recursively doing this through a number of steps. And what we get, so that's that step there, is we've got at some point we're going to bottom out and decide that we've got enough partitions. Maybe we've got some constraints, like there has to be a minimum area, or once the aspect ratio, like E is a particularly narrow, E and I are particularly narrow regions. We want to say, well, once the aspect ratio has gone beyond a certain value, then you don't want to risk partitioning it to be even narrower. Or you don't want to be partitioning it to go below a certain size threshold. Right, and then you've got regions which you can then use as the basis for some level design. So you might then either use those as the rooms themselves, they might be actual rooms in a house, for example, or they could be just bounding boxes for some other content where you might, they say, generate a room within this space. And you can use the tree that was kind of the tree which records the generative process, right? So we've got the fact that D and E were both children of B, right? We took B and we divided it into D and E. You can then use that to decide how you're going to put the rooms together. So if D and E have got a shared parent, you then put a corridor between the two of them. Okay. Yeah, so the corridors the inner nodes of the tree correspond to these things. Yeah, so it's quite a kind of, again, it's a general generative approach. You can design your own space partitioning algorithm to generate a particular kind of content. So it's a kind of a nice general idea you can use in your generators. I think that's another video probably from, so I go back to the PowerPoint, you can see that video working. So here we go, here's a nice video showing that process in motion. Okay. Okay, so I was wrong. We weren't on the last tool. We've got another tool in our toolbox, and this is quite a good one, actually. So this is the idea of Voronoi partitions, which is related to what I was talking about earlier with Delaunay triangulations. So this is a really nice technique for kind of like, it's going to basically another form of space partitioning, right? So binary space partitioning. We take the space, we divide it into two. We divide it into two again recursively as like binary partitions, recursively dividing into two. Voronoi partitions is another way of taking a space and dividing it up, but to get much more complex structures. And again, they can be used in all sorts of different ways in your generative process. So this is a really kind of great idea. So the basic idea of a Voronoi partition is that we have some 2D plane. or it could be 3D space as well. We could do this in 3D. But we've got some set of points which we define. So they could be randomly generated. Perhaps we're using a noise function to generate these, to lay them out in space. But we've got some distribution of points. Right, and you think about a constructed pipeline where we're successively building each step on some output from some previous step. It could be some previous generative process has generated these points. It might be these points are actually generated in a very particular way to get the kind of content we want, right? That's the beauty of these building blocks, is you can recombine them in all sorts of interesting ways. So we've got some partition, so we've got some distribution of points already in our plane, for example. The Voronoi partition is the idea that that plane can then be partitioned into polygons where there's one polygon per point, and that polygon is the region of the plane where those points are nearest to that point, right? So you can kind of think that each of those points owns a little region of space around it, owns a little polygon. Whereas if you're in that polygon, then you're closest to that point. Right, and depending on how we distribute the points, that already gives us a nice kind of natural looking, kind of slightly beehivey kind of bit of content. Right, so this is great for map generation. We can there's straightforward ways of taking a set of points and generating the partition, and there's actually some open source libraries available doing that in Unity. Right, so like I said, the distribution of points really kind of matters here. It's going to affect how that partition looks. So here we've got a truly random set of 2D points that we've generated. And true randomness looks really weird, so it's all kind of clumpy, and there's lots of perhaps that's the effect you want. Perhaps you want your level to look kind of craggy and clumpy, and that would be great. But you're going to get huge regions where there's just nothing. There's only one point with a massive polygon around it, and you get other regions where there's these tightly clustered things. Okay, so I'm going to go through a map generation process which uses Voronoi partitions as a kind of the basis of doing that. And this is all taken from this fantastic web page. There's the URL at the bottom there by a guy called Amit Patel, who's not only does he provide code examples to do all this stuff, he provides these kind of online kind of interactive generators where you can play around with this stuff and see how it works. Okay, so we can make things look a little bit more natural by starting off with something which is truly random, right? So that's easy to generate. But we can then kind of do an averaging process where we take each point, and that defines a polygon around it, but we then take some center point of that polygon, right? So we're kind of smoothing the partition out a little bit by doing this. And we can keep doing that iteratively to get an increasingly smooth process. So the more we do this kind of averaging of the corners of the polygons, then the more kind of regular it looks. So we can do this a couple of times, and it looks now a little bit more pleasing. It looks like a kind of set of regions which you could use as kind of basis for a map. All right, if we keep on doing this, we're going to end up with something which is very, very regular. Perhaps that's like what you want, perhaps it's not. Okay, so I think this after 2 passes, we can then start making decisions about what these regions mean, right? So for example, we could take things to be regions to be water or land, right? So you can do that perhaps based on some underlying reference image, right? So you might have another texture which defines height values, and you can take your you can perhaps generate that using Berlin noise. You can take that texture, you can overlay it with your partition, and then depending on the values for that each polygon, you might want to average those and say, well, if it's a certain amount of value within my polygon, then it's going to be land, otherwise it's going to be water. Right, you can then also look at whether things are connected. Is there a path from my water polygon to the edge of the map? If it is, then it's sea. If it's not, then it's obviously bound by land, so that's not sea, that's lake. We can then decide that We want our map not just to have, it's not flat land. We want some variation within our island, right? So this is, again, I'm describing a very particular kind of constructive pipeline for generating these kind of maps, but I'm hopefully illustrating what you can do with these kind of partitions. Right, so here we're taking our polygons and then varying the distance, so that basically varying the height of each of them. Right, so we're going to be saying if you're closer to the water, then you're more likely to be low level. We could have high level things there as well. We can choose how to vary the height, and the further away you get from the water, the more likely you are to be higher up. Right, so we get this nice effects where we're probably going to get a number of mountains or high regions, or maybe one or two or three, whatever regions within our island, which now are a high level, and they kind of gradually go down to the coast. Right, so we've now got height information. We've now got information about all these edges, about what the orientation and what the gradient is on each of those. Right, so we know starting from the highest points, where we go down from each point of those. So we've got that information. We can then use that to do things like start to seed rivers at the top regions, and then see how they would naturally progress down the vertices, right? And then we've now got a nice little path for where a river makes sense in our region, right? So we can start to randomly overlay different kinds of rivers by seeding different kind of springs, as it were, and then we can start to make decisions like, well, what kind of terrain is this based on how close it is to the sea, based on whether it's close to fresh water, has it got a river next to it, or there's no water around, perhaps it's a desert, that kind of thing. So there are all sorts of decisions being made here in this pipeline, right? So it's still this constructive pipeline, but at each stage, there's all sorts of decisions being made, and we could tweak these decisions to get all sorts of different kinds of map generation effects. Okay. Yeah, right. So that's a nice example of how you might use Voronoi in map generation, and I recommend going to that website to see demonstrations of this and also code examples. So this kind of stuff is actually used in real games. It's not just for that tutorial. So a really nice example of a game I like, which uses this, is called So Being Hunted. It's about 10 years old now, I think. But this uses Voronoi partitions to generate quite a complex island, using a similar process to the one we just saw. We start off with this kind of regular distribution of points, and then there's some random process which perturbs these a little bit. Then we take the Voronoi partition, then we use Perlin noise to basically decide to associate height values with each of the vertices, and that gives us this nice kind of island effect. And then there's a similar process to the one we just talked about, where you start to place towns, you start to draw roads between the towns, add rivers, that kind of thing. And you end up with quite a complex design for the island, which is actually then renders, as a complete level geometry, and dressed with things like hedges and trees and houses, depending on the decisions that we made for each of the particular tiles. I won't show the video for that, but you can look at the videos online if you want. Okay, so yeah, we get really quite a complex environment being generated using quite a simple algorithmic approach. Okay, here's another example of how you might use Voronoi. Here we've generated this Voronoi partition and used the edges as then the basis for a racetrack, right? So we just have if we can do a tour of those edges which loops around, then we've got a nice generated racetrack. We can kind of maybe smooth some of those corners out, depending on whether we want sharp corners in our racing game or not. Okay, that's another GitHub project, which is a nice example of using Voronoi map generation. Okay, so right, so I'm probably going to end on this. I think I could carry on talking for a lot longer, but this is going to be the last technique I'll cover. Okay, so this is the idea of wave function collapse. This is, I think, came out in about 3 years ago now. So this is an unusual example of a really nice general tool for procedure generation, which hasn't been around for decades in some form. This is a relatively new idea. So here what we're doing is we're taking, it's called wave function collapse, which is a rather grandiose name for something which is quite straightforward. So what we're doing is we're taking some kind of reference image. Right, for example, so say we're generating these tile maps, and the tiles are based on some kind of, what we're generating is, we're taking a kind of input map, and we're using that to generate a variety of new bits of content, which we could say look similar to our input. And the beauty of wave function collapse is that it's going to generate quite a diverse set of outputs based on just one or maybe a small collection of input content, right? So you can, as a designer, you can say, I want my plants to look like this, and you draw what might be in the second row there, right? You create that bit of content, say this is what the plants will look like. Wave function collapse will then use the kind of structure in your image, input image, to then generate a whole infinite variety of output images, apparently infinite variety of output images, which kind of retain the regularities you had in your input, but look different, right? So this is an extremely powerful technique, which you can use. As you can see, the same algorithm here is taking those inputs and generating a whole diverse set of outputs, and it can generate things from quite simple. So see the input here is just this little tiny little tile map, which is then that's used as a basis for creating a whole maze-like structure. Okay, there's some more examples of the other kind of textures that we've taken in, and here's one which is a little bit of a level down at the bottom. It's can be used to kind of generalize this to kind of generate a whole long level, which kind of has the same kind of regularities as what you saw in the input. So we've got this kind of like we've got this kind of input which is going to be sampled. So what wave function collapse is doing is it's basically generating new stuff which preserves the patterns it finds at a very local level. So it's got that input image, but it's going to be looking at tiny little samples of it. So we might take that input tile pixels as we've got in that image. We're going to sample them at say 3x3 grids, and we're going to be looking at all the 3x3 grids that we can find in our input. Right, so we're going to kind of like a convolutional network is going to do. It's going to scan our input with this little 3x3 window and look at each of those individual 3x3 grids that it finds. Right. So once you've done that kind of scan, you've got this now this collection of 3x3 grids. For example, you can choose to do grid size which is different. Which is each of them corresponds to a pattern, right? So what wave functions collapse is going to do is it's going to get you a new image which has similar distribution of these little patterns, right? So, for example, the same pattern, I don't know, if you put a picture of a level and it had just blue sky at the top, then as it samples your level, it's going to say, oh, well, here's just, here's 3x3 blue pixels. Here's another 3x3 blue pixels. It's going to count that twice, right? So that's two examples of one particular input grid. But it's going to get on and find other examples. So you're going to end up with a distribution, the patterns and how frequently you found them in the input image. Okay. So then when wave function generates a new image, it's going to try and do this, but following some constraints. And the constraints are quite clever. Basically, any pattern that you found in that occurs in the output should have occurred at least once in the input. So on a local level, looking at the little sections of your output, there's nothing there which wasn't in the input image, right? So every tiny little bit of your image was inspired by something which you actually had in the input. And then looking at how there's a distribution of these different patterns, right? So some of them occur more frequently, some of them are rare, some of them never occur at all. The distribution in your input should be basically similar to the distribution of the output, right? So the probability of finding a particular pattern in the output is related to how frequently it occurs in the input. Okay, so using these rules, you can wave function collapse is basically it's kind of this iterative approach where it figures out how constrained what the options are, right, for different kind of pixels based on these rules, right? So at the very beginning, you'll start with a blank image, and there's been lots of possibilities. But as soon as you start randomly deciding, okay, well, here's a bit of land, here's a bit of sky, it's the blue pixel, the yellow pixel, whatever. Then the rules then constrain what the possibilities are around it. And what wave function collapse does is basically keep on making choices about these things. As things get more constrained, you end up kind of painting the whole region in a way which is locally very similar to the input you had. So again, if you want to play around with this stuff, there's some great resources online. So here's an example of a project on GitHub which implements wave function collapse. Right. So yeah, this is an example of here we've got input image, quite simple, something that looks a bit like binary space partitioning. Might have generated it, and then you get this beautiful large dungeon generated using this process of gradually deciding how to fill in each of those pixels following the patterns you found in the input. Here's an example of it being used in a release game. It's an indie game called Caves of Quad, which was released a couple of years ago. It's quite popular and one of the first kind of games to use WFC in a big way. Right? It's kind of a roguelike game. And there's no reason you can't do this in 3D, right? So we were looking at 2D grids and sampling them with these n by n squares, these patterns, where you can do the same thing. You can take a 3D design and sample it using n by n voxels, as it were, right? So the tiles are now 3D, and you can use exactly the same algorithm, and it will be able to fill in this 3D world. Okay. Yep. So there's another. If you're interested in doing this as the GitHub I already showed you, but I'd also recommend going to the ProcJam website, which is a great game jam based around procedural generation, and there's a great tutorial on there about how to use WFC in Unity.